In chapter 2, we introduced the concept of a linear transformation. And a linear transformation was any function that happens between or happens to a vector or anything that can be expressed as a matrix times a vector. So in chapter 3, we start talking about those things and the theory behind them and the characteristics of them. All right, so the first definition, the first vocabulary word is the word image. Okay? The image. And we're also going to learn that some of the vocabulary words from previous math courses have been a little bit incomplete. Well, or a lot of bit incomplete. Okay? So some of the things we called stuff in Math 112 will have a little bit more precise meaning at this point. All right, so the image of a function consists of all the values that function takes in its target space. And target space is kind of a vocabulary word also here. In Math 112, this word image, we would have called it range. Right? So in Math 112, the word range would have corresponded to all the y values of a function. Now the word range really has a more precise meaning, and it's not one of our words. The word image is really the term for the set of all y values, the set of all outputs. Okay, so domain is still, in Math 112, domain was all your x values, all your inputs. That's what that word means. Okay, so the word domain means inputs. The word image means the outputs of the function. The word target space, the target space is where the outputs of the function live. Okay, so if we had well, let me keep writing. If f from x to y is a function, and the word function means some action that pairs input with output, some action that you take and you do to something that's a member of x, and it transforms it into something that's a member of y. And in this class, transforming it means multiplying it by a matrix. Okay. But if f from x to y is a function, okay, x is the domain, y is the target space. Let's put a little note of that. All right, so in symbols, the definition for image, all right, image of f, im of f. In set notation, the image is a set, all right? It's the set of all f of x We could write it as the set of all B, such that B is an element of Y and B equals f of x for some B is f of something. All that is fancy speak for it's the outputs of the function. Image is the outputs of the function and only the outputs of the function. So if we look at a Math 112 example, I always like to do that. Math 112 example. Our function f of x equals x squared. Okay, f is a function that takes a real number and gives you out a real number. Right? You take a real number, you square it, and you come out with a real number that was something squared. That's what this function does. All right. The image, if we characterize what the outputs to this function, when I say characterize, describe the outputs to this function. Okay, stuff squared. Tell me something about stuff squared. Stuff squared. Stuff squared is always negative, right? Yeah, when I multiply a number times itself, I always get something negative. No, of course not. That would be a ridiculous thing to say. When you do something squared, you always get a positive number. Okay, so we could, if we look at the graph of y equals x squared, the image is the set of all the outputs. That's all the y values. That's all the positive real numbers. So the image of this function, we could say r plus, r positive real numbers. Or we could, if we wrote it in set builder notation, we could say the set of all x such that x is greater than or equal to 0. A lot of different ways we could say that. We could write it in interval notation and say 0 to infinity. Whatever. I probably should have used a y instead of an x right there. Whatever. I wasn't thinking in terms of x's and y's. I was just thinking in terms of set of things such that things are bigger than or equal to 0. That's image. The target space is real numbers. That's where the positive real numbers live. Now, these terminologies are not really absolute. Like, is that absolutely the target? Well, the real numbers live in the complex number system. So could the target space be the complex numbers? Yeah. So there's a little bit of ambiguity there. But if this classroom full of people was the universe, and the image was the set of brown-headed people, right? Target space, this classroom. Image narrowed down a bit. Sometimes the image and the target space are the same. Let's draw a picture. So this X, that's the domain. That's just the region of the universe where the inputs to this function live. And over here, we have a bunch of little X vectors that live in our domain. X1, X2, X3, and so on. However many of them live there. So we got a bunch of Y values. The function is what maps them to each other. In this class, this F is the act of multiplying a vector times a matrix. In Math 112, the function was the act of taking the number and multiplying it times itself. Right? A function is a verb. A function is an action. A function is what happened to take thing over here and turn it into thing over here. Here's the image. The image is this region of the target space where only the outputs live. Notice how there's other space over here. There's other things that live outside the image in the target space. Which is not always. Sometimes the target space, sometimes the image fills up the entire target space. But the image is a subset of the target space. The inverse function would map you back. Now I've drawn the way I've drawn this, there wouldn't really be an inverse because it's not one-to-one. You got two X values corresponding to one Y value. So there's not really an inverse. We're just talking terminology here. I'm not necessarily being 100% correct. I better get rid of that or somebody will see it. I'll lose all my linear algebra street cred. So that's our first bit of terminology. All right, if we graph the function f of x equals e to the x, what all the y values look like. Negative numbers, right? When I take e to a power, I always get a negative number. E is 2.7 something. When I raise 2.7 something to a power, I get a negative number. They're all positive. Now there's a slight difference in this one and this one. All the outputs are positive. What power can I raise E to and get 0? 2.7 something to what power equals 0? None. You can't raise a positive number to a power and get 0. There's no such thing. So on this one, all the outputs are positive and not 0. So the image of this function would be, in interval notation, we could say 0 to infinity with a parenthesis. Or we would say the set of x such that x is just greater than 0. Not equal to. The target space is R, all the set of real numbers. Well, I haven't done the ceremonious adding of the page breaks. "40 pages ought to do it." All right, let's consider this function. And this function is going to map things from R to R2. So R is real numbers. R2 is the set of all two-dimensional vectors with real numbers in it, the XY plane. Okay. And this function is defined as f of t is the vector cosine t sine t. Those of you who have had calculus or calculus 3 or are in calculus 3, this is what's known, this is a vector valued function. You probably didn't see it as a column in calculus 3, but you probably would have like an I hat or a J hat. All right, so let's talk about what this is. We plug in a t value and we get out a vector whose x coordinate is a cosine and whose y coordinate is a sine. So if we characterize f, all right, plug in real numbers, get out You plug in real numbers, you get out two-dimensional vectors whose x coordinates are cosines and whose y coordinates are sines. Let's draw a few of these things. All right, so if t were 0, cosine of 0 is 1, sine of 0 is 0. So we would have, if t was 0, we'd have the vector 1, 0. All right, if t equaled pi over 4, all right, we'd have the vector that ends at point square root of 2 over 2, square root of 2 over 2. Right, that's the cosine and the sine of pi over 4. All right, if t were pi over 2, we'd have the vector 0, 1. What am I forming? The unit circle. The equation of the unit circle is x squared plus y squared equals 1. The parametric equations for the unit circle, x equals cosine t, y equals sine t. That's the set of outputs. Everything that's an output for this function is any point along the edge of the unit circle. Now, in this case, our image is not the set of y values. It's not the set of the y values for the unit circle. That would run from -1 to 1. Okay? It's the set of vectors, right? Because we're talking about living in 2 dimensions now. So if we wrote that as a set, I don't want to write it as a set. I'm trying to make a mountain out of a molehill. It's a unit circle. All right, here's an important statement. If f is invertible, then the image of the function equals the target space itself. Right? If I drew this picture, there's a one-to-one correspondence. Everything in the target space gets mapped to and maps back. Notice how the arrows are double-ended. It maps both ways. F goes one way, and then F inverse goes the other way. If you don't have that one-to-one correspondence, you can't map back. Because somebody'd have two arrows or no arrows coming in. Let's look at another one. Consider transformation T that maps from R3 to R2. I'm sorry, not R3 to R2. It maps from R3 to R3. I can't read my own handwriting. And here's this transformation. It takes a member of R3, a three-dimensional vector with real numbers in it, and it turns the z coordinate into 0. I need to say the x3 coordinate instead of the z coordinate. If I call it the z coordinate, then I'm limited to 26 dimensions. That's just not enough. So this transformation is the act of zeroing out the third coordinate in the vector. And that can be expressed. There's a matrix that'll make that happen. I can't think of what it is off the top. But if we characterize this, let's draw a picture. Let's draw a picture of R3. We got the x1 axis, the x2 axis, the x3 axis. X, Y, and Z axes. Okay. The XY plane is laying on the table. The Z axis is sticking straight up. All right. Now, if I just take some old generic member of R3, we'll call it X. X1, X2, X3. Does that light blue show up good enough? Do I need to change that? All right, and I do this transformation to it. Then what I'm going to get and I do this transformation to it. I'm going for it's taking it and it's shoving it down on the XY plane. Okay, so what we are looking at, this transformation is projection onto the X1, X2 axis, X1, X2 plane. Okay, so if we were hovering up in space up here close to the format background button up here, shining a flashlight, a powerful flashlight down down the x3 axis, our transformation vector, our fuchsia vector here would be the shadow of the blue vector. That's an orthogonal projection. It's shadow. All right, so if I took every possible stinking member of R3, every three-dimensional vector with real numbers in it, every possible member of R3, and I did this transformation to all infinitely many of them, I spent all of eternity turning z coordinates into 0 and plotting them on the x1, x2 plane. All right. What would I get? So if I just started turning three-dimensional vectors into their shadow. There's one of them, 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 and I just keep going for all of eternity. What would I eventually do? Eventually, I would color in the entire x1, x2 plane with endpoints of vectors. Eventually, the entire plane would be carpeted, blanketed with endpoints of vectors whose z-coordinate is 0. That's the image, the set of all possible outcomes. So the image of this transformation is the x1, x2 plane, the xy plane. We could even say the image is R2. We're not going to say the image is R2, by technicality, because you could think of all the two-dimensional vectors as three-dimensional vectors whose z-coordinate is 0. But we have expressly written it as a three-dimensional vector. So that's R3. Question there. All right, we've got a transformation T of x equals matrix A times x, and we're given matrix A. All right, so let's do a little bit of, characterizing here. T of x equals 1, 2, 3, 6 times x. This is a 2 by 2. What must x be? Well, it's a vector, so something by 1. It's got to be 2 by 1, right? We can't multiply 2 by 2 times a 3 by something. The inner dimensions don't match. Okay, Now, what does that tell us? That tells us, so this right here tells us that our domain is R2. Our inputs are two-dimensional vectors. This part, the outputs are 2 by 1. So our target space is also R2. So all that to say, okay, well, T extends from R2 to R2. You take in a two-dimensional vector, you get out a two-dimensional vector. Yeah, that's great to know. Now, moving on with our life. It is important to know because you need to know what kind of animals you're going to get out. You need to know what you're putting in. You need to know what you're getting out. Okay, let's characterize this transformation. So T of X, 1, 2, 3, 6, times something like this, X1, X2. When we do that multiplication, we get X1 plus 3X2, 2X1 plus 6X2. That's a vector, not a matrix. Well, a vector is a matrix, but that's a 2 by 1. That's not a 2 by 2. X plus 3X2. That's one item. It's a vector. We could rewrite this like so. Okay, so we started in matrix form, we multiplied it, and then we went to vector form. Some of that old vocabulary coming back up. We could bring a 3 out of this one. We could rewrite that as X1 plus 3X2. We could do that. We're just dealing with scalar multiplication. That's legal. So when we do this transformation, all of our outputs will be of the form x1 plus 3x2 times the vector 1, 2. All of our outputs, or T of x's, will be of the form x1 plus 3x2 times vector 1, 2. What kind of animal is x1 plus 3x2? Individual little x's are real numbers. So real number plus 3 times a real number. All right, 1 plus 3 times 2 is 7. Negative 5 plus 3 times 1. Wait, negative 5 plus 3 times 1 is negative 2. Whatever I plug in for x1 and x2, I get out a real number. A real scalar. So we can refine this statement. The image of T is the set of scalar multiples of 1, 2. We don't really need the x1 and the x2. I mean, you can make any scalar out of x1 plus 3x2 if you're allowed to have any real numbers for x1 and x2. So our image is the set of all scalar multiples of vector 1, 2. We'll put a little caption. The set of all scalar multiples of the vector 1, 2. What does that look? Let's talk about what that looks like. We're living in R2. All right. Vector 1, 2. There it is. I really need my virtual graph paper up here right now, but it's not worth opening it up just for one problem. Vector 1, 2. Let's do a scalar multiple of it. 2 times vector 1, 2 is 2, 4. All right, 1/2 times vector 1, 2 gives us 1/2, 1. Negative 1 times vector 1, 2 gives us negative 1, negative 2. The endpoints of all these vectors are landing on the same line. Y equals mx plus b. B is 0. Y equals mx. Y, rise over run. M is 2 over 1. Y equals 2x. That's the image. The line y equals 2x is the image of this transformation. So which is it? Is it this or is it this? Yeah, either one. Different ways of saying the same thing. Either one says what all the outputs look like. Whoa, that didn't need to happen. All right.